So finally then we come to the miracle year. Miracle year of 1905. Again, you would not look at Einstein's life here. Certainly he was a good physics student. Look at his career so far, and this would be totally unexpected that this would happen. He had been able to publish a few physics papers in German journals, but nothing extraordinary. So let's just take a look at the miracle year itself here and talk about, briefly, the 5 papers that he published in the miracle year. So, March 1905, and we're just going to give a brief summary of each. Obviously, one of them, the one that dealt with what became known as the Special Theory of Relativity, will be our focus in this course. But in March 1905, he published a paper that essentially introduced the idea of the light quantum. So this was one of the seminal papers in quantum mechanics. And of course, the theory of quantum mechanics came to dominate much of physics throughout the 20th century. And Einstein was there at the beginning. It was what he called a heuristic proposal, because you might say, well, what is a light quantum? Essentially, it's treating light as a particle. But you think, well, what about the wave theory of light? That was well established by this time, 100 years or so after Thomas Young had proposed a more modern wave theory of light. Earlier versions had existed as well. So here was Einstein going back essentially to a discredited idea. And how can you have light as a particle when the wave theory of light was so well established? Well, he said, I know all that, but you know what? The wave theory of light really deals with light as it's traveling. We're not quite sure what happens when something emits a wave of light, a light wave, or absorbs light. And so this is what he was dealing with at this point. And he essentially called it a heuristic proposal. He said, let's just try it and see what happens. And he was able to, using this idea, was able to show that some experimental results that couldn't otherwise be explained were explained by his idea. So the idea of the light quantum, that's in March. Next month, April 1905. This is all 1905, so I guess we don't need to put the years, but we will. April 1905, published a paper that actually became his doctoral dissertation. This was his essentially at least a second attempt at a doctoral dissertation. He had a couple other attempts that never got anywhere. And of all the papers that he published in 1905, this is maybe the most, you wouldn't call it ordinary, maybe mundane, but it is a paper demonstrating that you could actually calculate the size of molecules. Other people had done similar calculations. He came at it from a different direction, and through some fairly sophisticated calculations was able to demonstrate, for example, the size of sugar molecules suspended in water. Came up with a theory of how to do that. This actually became the most cited paper of all of them in 1905 because it had many practical implications in terms of just any time you have grains of things or solutes in solvents and so on and so forth. So size of molecules, good solid paper, not revolutionary, but certainly influential within its context. So that was April, just 1 month apart. Now we get to May, the next month. Any one of these papers would have been a good paper just for a year's output, but he's now in May 1905, and what he does is publish a paper that for the first time provides really good theoretical proof of the existence of atoms. And it came about because he was able to explain a phenomenon known as Brownian motion. Brownian motion goes back to a guy named Brown, actually, in the 1820s, 1830s. And what the observation was that if you take maybe dust particles or pollen particles in water and you look at them under a microscope, the particles sort of jiggle around, they zigzag, And the question is, early observers who saw that thought that the particles might actually have some sort of vital force in them. They're actually some sort of organic force going on. But Brown and others were able to show that it really happened no matter what it was. You can put rocks, little bits of rock and sand and so on and so forth, and you still get the same effect. And it came to be known called Brownian motion. So the question is, how do you describe something like that? What's going on? And what Einstein was able to do, using actually some of the techniques he developed in this paper on the size of molecules, where he imagined sugar molecules, larger sugar molecules suspended in water among the water molecules. He applied that to Brownian motion, some of those same techniques. And so you've got the pollen particles being the larger entities there within the water or whatever. And he applied some hydrodynamic theory and so on and so forth. And essentially came up with the idea that the motion of these particles that you could actually track. So you would actually look at a little particle here and you observe it over time. And it'd be over here, and then maybe over here, and then there, and then over here, and so on and so forth. And you sort of get what later became known as a random walk. And Einstein developed a theory that explained that, and also was able to sort of put it together in a way that became very easy, or relatively easy, for experimentalists to try to verify that. In fact, right about this time as well, a couple of years before this, the so-called ultramicroscope was developed, which allowed people to really about 50,000, there's an increase of 50,000 times or so in magnification. And they were able to apply it to the Brownian motion problem. And within a few years had demonstrated that, yes, Einstein was right. And so, whereas you might think, well, people had talked about atoms forever. In fact, going all the way to the Greeks, going all the way back to the Greeks, people had talked about atoms. But even at this late date, this is after the existence of the periodic table of the elements developed in the later 1800s, and John Dalton's atomic theory earlier in the 1800s, and so on and so forth. There was still a lot of skepticism that atoms actually existed, and in fact, whether they were even a proper entity to inquire about for scientists, because you could never see them. How could you ever imagine to see something as small as an atom? So maybe we shouldn't worry about atoms themselves, but look more at the bulk properties of matter and seek to explain that way. Well, Einstein actually was able to show theoretically that there was pretty convincing proof atoms existed. It was backed up a few years later by experimental proof. And here's actually where Ostwald comes into our story again. Wilhelm Ostwald, who we just talked about, Hermann Einstein's letter, Albert's father, letter to Professor Ostwald. And he was one of the holdouts. He was a very strong skeptic of atoms. And yet Einstein's work, plus the experiments a few years later, convinced Ostwald. So he had a very well-known textbook on physical chemistry, and as late as 1905, 1906, 1907, he was still saying, there's really no good evidence for the existence of atoms. By, say, the 1908, 1909 edition, he had changed his tune on that. So, May 1905, that paper, Existence of Atoms. Now we're into June 1905. And this is the paper on the special theory of relativity. It was actually, the title of it dealt with the so-called electrodynamics of moving bodies. We will actually be looking at that paper. I'll have you read it if you're doing the more quantitative approach to the course, to read it, not to try to understand all of it. Actually, the physics and math involved isn't that complex, but is beyond, some of it at least is beyond our course. But, and if you're doing the qualitative approach, it's optional if you want to read that. But just to get a sense, what's his argument here? What are the sections? Outline the paper, see what he's trying to do here, and then we'll talk later on a little bit more about the details there. So the electrodynamics of moving bodies there, Special Theory of Relativity in June 1905. And there's a famous line here. Einstein had been thinking about this for a long time, and there's a key contradiction that he just could not get his mind around. Again, we'll talk about the details later on. But he had a a friend at the patent office named Michael Besso, and they often would go out during lunch break. He worked at the patent office 6 days a week, 8 hours a day, had a lunch break there as well, so 9 hours if you include the lunch hour. They'd often go walking and talk about the latest physics problems that Einstein was thinking about, and Besso as well was trained as an engineer, and he and Einstein had known each other for a number of years. And so they're talking about some of the conundrums, some of the puzzles involved in this, and the whole electromagnetic worldview we talked about a little bit. And finally, something Besso said. We don't know exactly what he said, but the next day Einstein came back and said, I have it. Essentially, what you said, cleared everything away, all the cobwebs away, as it were. And in later years, Einstein described it this way. He realized that time is suspect. There's something about the nature of time itself that he and a lot of other people had overlooked. And so that will be one of the key things we'll be investigating, this whole idea. What does it mean to say time is suspect? Why is time suspect? That's June 1905. And as we're doing this here, as we're thinking about this, don't forget the context here. He's working in the patent office. This whole idea, time is suspect, every day almost. He's probably reading patent applications dealing with time and dealing with telegraph signaling systems, and the synchronization of clocks was a huge issue at this time. So there's no direct connection necessarily between the expansion of the railroads, telegraph, synchronization of time, standard time zones, and all that, yet it provided the context. And perhaps there's something unconsciously that led him to these insights, as well as a number of other factors coming in there. So that's June 1905. Then one more paper in September 1905. And essentially this is an addendum, a coda, to the June 1905 paper. He says, I've been thinking more about that paper I wrote a few months back. And there's some interesting implications of that. And essentially, the key one is E equals mc squared. Einstein didn't quite write it like that, but that's essentially what it is. Energy equals mass times the speed of light squared. Most famous equation, certainly in the world, and really just sort of a tacked-on paper to an earlier paper here. So, definitely the miracle year. This unknown 26-year-old patent clerk, seemingly out of nowhere, comes up and publishes 5 papers that any one of which could have made his career, certainly, in the physics world. And yet, in a real sense, certainly the light quantum paper, the special relativity paper, the E equals mc squared paper, the existence of atoms paper, these had profound implications for how we understand physical reality. And even the size of molecules paper, certainly, as I mentioned, most cited paper of all of these, and it's one of the most cited papers of its time. So an astounding year. And yet, even though all of this happened, later on in the course we'll say, how did people receive this? Especially, how did people receive this idea of what became known as the special theory of relativity? And it was a mixed result at first, a mixed reception. In fact, there was strong evidence right off the bat that the theory might be dead on arrival because there were experimental results that said it was false. And so later on in the course, near the end, we'll look at that, see how Einstein responded to that, and see what happened in later years after his miracle year, which certainly rivals Isaac Newton's miracle year for its miraculousness, I guess you could say. So hopefully that gives you now an idea of how Einstein came to 1905, some of the key trends we see in science and technology of this time, and then Einstein's own particular context, despite being in sort of a turmoil with his family, with his girlfriend, getting pregnant, jobless, wondering if he's going to find anything, still is able to persist and persevere and show resilience and grit, in a sense, and focus in on his physics, that those powers of concentration. So this did not come out of nowhere. Sometimes we think miracle year, and we talk about like 5 papers in 5 months. So he just started thinking about perhaps in January, and all of a sudden this poured forth. No, this was a long period of preparation. He'd been thinking deeply about a lot of these matters for a number of years, certainly since the mid-1890s. So for at least 10 years, he'd been working on these things. And it was just the way it worked out. The insights sort of tumbled out during this year of 1905. So what we'll be doing next then is, and really for most of the rest of the course, is looking more specifically at the special theory of relativity and trying to understand it sometimes in a quantitative sense, but certainly in a more qualitative sense as well, so that we can follow in the footsteps of Einstein. And really, as we started the course with the idea that just to peel back a little bit of the mystery of the marvelous structure of reality, as Einstein put it, and as Einstein sort of showed us the way here.